So as I mentioned at the beginning of the online lecture for Chapter 2, living organisms obey the same universal laws of chemistry and physics as non-living things. And we're going to explore a little bit about why that is, specifically as it relates to energy and energy transformations, in this last part of online lecture number 2. Living organisms require energy, and because we want to understand how living organisms work, we need to understand these universal laws that relate to energy. So we know enough about energy dynamics in our universe that there are actually scientific laws to describe energy transformations. And we're going to consider the first two laws, and these are called the laws of thermodynamics. The first law states that energy is neither created nor destroyed. So even when energy is converted from one form to another, the total energy before and after the conversion is the same. So this poses a real problem for living organisms if no energy can be created or destroyed. So energy then has to be obtained from somewhere where it's already pre-existing. And so some of you may be familiar with the idea of potential energy in terms of, say, a ball rolling down a hill or maybe even water behind a dam. But in terms of potential energy that can be used with organisms, we're generally talking about. But in terms of energy that can be used by organisms, we're generally talking about the energy that's stored into chemical bonds. So for this snake, that meat and that rat it's eating represents potential energy. So what happens during metabolism is that potential energy that's stored in chemical bonds will be converted to kinetic energy or another form of potential energy. But because of that first law of thermodynamics, the total amount of energy before and after consuming that rat is actually the same. However, that energy must continuously be replaced. The snake can't create new energy, but it continues to require it for metabolic processes. So we also know that in terms of energy, that the amount of useful energy in the universe is actually decreasing, and the amount of disorder, or what we call entropy, is actually increasing. So what this means is that some energy is spontaneously transforming from potential energy into useless energy. Thus, the universe is sort of tending towards disorder, and any process that requires order must fight against this. Therefore, any process that tends towards order, so against this tendency of the universe to head towards disorder, costs energy. So this is why body processes require energy, because cells are quite orderly and must spend a lot of energy both to establish and maintain that. And you're probably familiar with this if you think about cleaning your own bedroom. You know that letting the room get messy, that sort of happens spontaneously and doesn't require a lot of work on your part, but that to organize it actually does require energy. And so I like this cartoon over here because it's sort of showing one of the major obstacles faced by living organisms. And that is, requires an input of energy to maintain life. So it's like you're always having to run uphill, where the natural tendency in the universe is for energy to actually move towards a disordered state. The problem with this disordered state is that energy is then not useful to do work. So let's take a look at how these two laws fit together and see what we can do to form an overall understanding of energy transformation. So the first seesaw up here shows the first law of thermodynamics, and what you can see is that the energy before any kind of energy transformation takes place is the same as the energy after. That's because energy can neither be created nor destroyed. All it can do is change form. What I want you to think about in this diagram is that this blue energy is useful energy. It's usable. It's something that cells can use to fuel metabolic processes, that you could use to clean your room, for example. And we're going to call that free energy. And you'll see that after an energy transformation step, that the amount of free energy overall has actually been reduced. But the total amount of energy is the same. The reason for that is that some of the usable energy has been converted into unusable energy, or what we call entropy. And of course, over time, the universe is actually heading towards a completely disordered state. But that's going to be way beyond our lifespan, so we won't worry about that. But what this second law of thermodynamics shows us is that energy processes are inefficient. So we, as living organisms, cannot harvest all the usable energy out of any food source that we might consume. And in fact, we know that it takes about 10 kilograms of food in order for 1 kilogram of animal body growth. So you can see from our discussion that there are some reactions that are going to require energy and some that are going to release energy. We call chemical reactions that release energy exergonic reactions. And we talk about this energy in terms of the free energy, that is the energy that's available to do work. So you'll often see this symbol next to a chemical equation. This is delta, which stands for the change, and G, which actually stands for Gibbs, but together this is the symbol for free energy. So we talk about the change in free energy, how much was available before a reaction took place and how much was after. If free energy is released during the course of a reaction, then that reaction will have a negative delta G value. Catabolic processes fall in this category, and these are reactions where the complexity decreases, leading to an increase in disorder. Remember, though, there's no change in the total amount of energy that's available. What's happening is a change in the amount of free energy. Reactions that consume energy are called energonic reactions, and they have a positive value of delta G. Anabolic reactions would be an example of this, and these are situations where complexity increases. So, for example, like in the formation of a polymer during a condensation reaction. So these graphs can help to understand what's happening with free energy in an exergonic reaction. During an exergonic reaction, free energy is released, and this means that you can sort of think about this reaction as one that would roll downhill. It's sort of following the natural tendency of the universe. Energonic reactions, on the other time, are situations in which the energy of the products is higher than the energy of the reactants. So what is required is an energy input of some sort. So this would be tending towards order instead of disorder. And in cells, both endergonic and exergonic reactions take place, and they often do so simultaneously. So this chart shows some delta G values for some various reactions, but the sign has been left off intentionally. And so I'd like for you to look at these reactions, and based on their description, and also just looking at the reactants and the products and how ordered or disordered or simple and complex they are, I'd like for you to decide whether these delta G values are likely to be positive or negative. So this concludes our online lecture 2. There will be a quiz on this material on Wednesday, and I thank you for listening to these lectures. Please contact me if you have any questions. Have a great weekend.